Good morning. Welcome to the summer camp course, A Bridge to Career in High-Tech Industry, a summer camp on integrated circuit design. My name is Payam Haydari, and I'm the director of Nanoscale Communication Integrated Circuits Labs at the University of California, Irvine. Let me just share with you a brief introduction of myself and my research at UCI. I'm the University Chancellor's Professor. You can find more information about the fun research that we are doing in my labs, both in my personal web page as well as the lab web page, where we include all the recently published works, all the interesting news that have come out of our group and the lab, and you're more than welcome to visit the lab website. My research primarily covers the design of terahertz, millimeter wave, radio frequency, analog and mixed signal integrated circuits. I have been fortunate to cooperate and work with a number of very bright students. I have been fortunate to supervise these students, 39 as a result of our research activities. 39 students got their PhD under my supervision. Overall, 39 PhD and master students got their degrees under my supervision. Currently in my labs, I'm supervising 7 PhD students. Okay, so what is covered in this course? As I said, we try our best to make sure that the course stays interactive. I would be more than happy to engage with you in any question that you have, spanning from the course material, and also if you have any question about the current state of affair in semiconductor market, in general high-tech market, I would be happy to share my thought. First, the course will go through an intuitive understanding of structure of a MOS device. MOS stands for metal oxide semiconductor technology device. This is the predominant technology that is used to implement a transistor. We will discuss the regions of operation, in particular, a strong region of operation, which we call a strong inversion in MOS device. I will discuss extensively about the operation of MOS device in the so-called triode region of operation and saturation region of operation. Then I will switch the gear to the analysis, simulation, and layout of CMOS single-stage amplifiers. I will look at the operation of commonly used single-stage amplifiers, including common source, common gate, and cascade amplifier. If time permits, I will also share with you the design of differential amplifiers. We will also discuss the simulation layout of these widely used single-stage amplifiers. At the same time, I will also introduce the basics of a digital CMOS inverter. That includes analysis, simulation, and layout of these structures. I will go over the transfer characteristics of a basic CMOS inverter. Then I will describe the concept of noise margin and will analyze the propagation delay of a basic CMOS inverter. This analysis, namely the analysis of propagation delay, gives us a very good insight and intuition about the large signal behavior of a CMOS inverter. I will also go over the analysis, simulation, and layout of basic combinational logic circuits that are widely used in a digital integrated circuit. That includes the structure of a NAND gate, how it is laid out in a CMOS process, a NOR gate, and an XOR gate. And also, toward the end of the course, I will discuss the implementation of an arbitrary Boolean logic function in a CMOS process. Okay, so I would like to, as a motivational point, together we go through the state of affairs and the current status of major high-tech companies and their position in the whole US and global economy. As of June 2023, I have listed a number of extremely famous high-tech companies and semiconductor companies, high-tech companies with a strong and large group of IC designers. Apple, of course, is the most valued high-tech company in the world with a market cap of $2.83 trillion. I would like to reiterate that these numbers are reported based on the June 2023 report of these market caps. Samsung, another famous high-tech company, has $472 billion of market cap. Alphabet and Google, traditionally been known as a search engine company, but they have also a strong group doing various types of activities revolving around IC design with a market cap of $1.57 trillion. Of course, the other familiar names in the market, particularly in semiconductor, big players include Intel with a market cap of $132 billion, IBM, which is right now a service / enterprise company with $117 billion of market cap. Of course, we have heard of NVIDIA and all the craziness around the obviously steep growth of the NVIDIA. Just yesterday, the company touched the threshold of $1 trillion market cap. The two other companies which have a strong presence in Southern California include Qualcomm and Broadcom. Why did I mention all these companies? Just wanted to say that the big contributors to both the US and the global economy are in fact high-tech companies. And this is the best time, in fact, one of the best times to be involved in high-tech industry, in integrated circuit design, particularly in analog and digital, primarily because of the rise of AI and artificial intelligence, machine learning. You may wonder why all of a sudden ML and AI would be a big determining factor to the hotness and high demand of IC designers. This is simply because as the data sets of machine learning and AI complicated, sophisticated algorithms will be increasing, there is a need for a processor, a computing infrastructure, and module to be able to handle all this sophisticated computation. And it turns out, interestingly, that as of like 2 years ago, analog computation, interestingly, proved to be more power efficient and higher performance compared to a widely used digital computation. That means that the analog computing is basically turning it's becoming one of the major candidates for next generation high-speed graphic interfaces and accelerators, particularly for machine learning. So as you can see that, there are some emerging applications that make the job in IC industry, analog and mixing and digital circuit design, particularly interesting and exciting. Shown in this graph is the sales in billion US dollars with respect to the year under consideration. And as you can see, there is considered to be healthy superlinear growth of market and sales of the IC products as we proceed to the latest years. And you can see that this healthy growth will continue. And as I mentioned in the previous slide, with the rise of ML and AI, particularly as you are familiar with search engines and intelligent search services such as ChatGPT, I anticipate that the need for high-speed, high-performance computational engines, primarily based on analog, mixed signal, and digital integrated circuits, would be rising and continue to rise, contribute to this ever-increasing demand for semiconductor sales. By the way, I gathered the information from this website. You are more than welcome, once I share the slides, to take a look at the article related to this table and to this projection. Okay, so almost all high-tech industry have now a strong IC design team, which could be in the range of few hundreds to, in fact, few thousands in the case of Apple. For example, Apple, even like 10, 12 years ago, their IC design group was not really considered to be a huge part of the entire company. But right now, I can say in excess of thousands of employees and circuit designers currently working at Apple, positioning this company as one of the biggest IC design companies in the world. The other companies which are familiar is Samsung, even Microsoft. Microsoft is an operating system, primarily software company. But again, they have a strong and emerging group in IC design. I mentioned Google, of course, Intel, which with its primary product on digital chips, digital integrated circuits and processors. MediaTek, a big company that produces ICs in radio frequency radios for a number of applications, including Wi-Fi and cell phone. NVIDIA, which is primarily a graphical processing interface and also the analog and mixed signal engine for ML and AI. Texas Instruments, mainly providing the chips for digital signal processing. Broadcom, with a whole range of integrated circuit products covering many industries, including enterprise, including wireline, copper backplane, fiber optic products. We have a Skywork, which is with its headquarters just in the back door neighbor at UC Irvine. They have also an expertise and huge market in power amplifier module, semiconductor module for radios, and for antenna interface, heavily used in cellular market. There are some other companies, IBM, for example, even Facebook or Meta. It is surprising that even Facebook has a strong group doing the IC integrated circuit design. Other companies including Cisco, Oracle, Qualcomm, NXP, Uber, big group in radar projects or radar design, IMEC, which is a big research centers in Europe, and Lyft. These two companies, Uber and Lyft, also put together a strong group doing radars, radar chips, radar on chip for a number of applications. So as you can see, pretty much all the high-tech companies have either a major focus on integrated circuits or have a strong, large group doing IC design for their applications and for their products. Okay, so we are located at obviously Orange County. University of California, Irvine is midway between Los Angeles County and San Diego County. And not only we have our own industry, primarily focusing on communication / biotechnology / even MLAI products, but also we can benefit from a growth market in Los Angeles and San Diego County. In terms of the local high-tech companies, there are many companies that have either their headquarters here or they have a big research center in circuit design, the IC design group in Orange County, including Intel and Tower Semiconductor with their big foundry doing a specialty semiconductor manufacturing. We have Broadcom, Skyworks, as I said, their headquarters is in university campus, literally in university campus. We have MACOM and MaxLinear. MaxLinear is dominating the market in the TV-related integrated circuits and products. Apple, they have also built and opened up a center in Irvine. We have Qualcomm in San Diego, Marvell in Irvine. Google, of course, have a center in Jamboree in Orange County. We have Microchip. They have also big presence in Wi-Fi applications and cellular applications. We have Western Digital, Amazon, and SpaceX. SpaceX, they have a very big IC design center in Orange County. So as you can see, the presence of IC industry is very healthy in Orange County, making it possible for everyone who pursue their future career in IC design to pick and choose one of these companies. Okay, finally, I would like to share with you another graph that exhibits annual growth of various products in IC industry. So if you look at the products, and by the way, I got this from the IC Insights, this graph, you see that for many IC industry, many IC companies, analog product constitutes a big portion of the products that they are offering to the market. The semiconductor IC industry, therefore, are still a major player in the whole US economy and the global market. Almost all high-tech companies now have dedicated IC design groups. With that being said, I would like to stop here and find out if you guys have any question before moving on to a video that I'm going to share with you about the semiconductor manufacturing.
All chips start out with a very simple raw material, sand. Sand is primarily made up of silicon dioxide, or silica. Silicon is the second most abundant element in the Earth's crust, but is only ever found as a compound with oxygen. Complex chemical and physical processes are required to ensure that silicon crystals meet the high production standards that apply to chips. To convert silica sand to silicon, the sand is combined with carbon and heated to an extremely high temperature to remove the oxygen. A number of other steps are required to create the finished product, namely an extremely pure monocrystalline silicon ingot called a boule, with only one impurity atom for every 10 million silicon atoms. Silicon boules are fabricated in a range of different diameters. The most common sizes are 150, 200, and 300 millimeters. Wafers with large diameters offer more space for chips. Extremely thin wafers are then cut from the silicon boules using a special sawing technique. These wafers are the basic building blocks for subsequent chip production. Silicon is a semiconductor. This means it can conduct electricity and also act as an insulator. Its atomic structure looks like this. Every silicon atom has 4 outer electrons. There are no free charge carriers. As a result, the pure monocrystalline silicon is non-conductive at room temperature. To allow it to become conductive, small quantities of specific atoms are added as impurities to the wafer. These impurity atoms must have a number of outer electrons that is either one more or one less than that of silicon. Silicon is in the 14th group of the periodic table of elements. This means that elements in the 13th or 15th group have to be used in this process, referred to as doping. Boron and phosphorus atoms are the most suitable elements in these groups. They are very close to silicon on the periodic table and therefore have very similar properties. Phosphorus has 5 outer electrons. When it is inserted into the silicon crystal lattice, the 5th phosphorus electron can move freely. This means that the silicon phosphorus crystal is N-conductive. In contrast, boron atoms only have 3 outer electrons. When they are introduced into the silicon lattice, one silicon electron has nothing to bond to. This creates electron holes. The holes move through the crystal like positively charged particles, making the material p-conductive. Transistors are built on the p and n conductive layers that exist in a doped wafer. Transistors are the smallest control units in microchips. Their job is to control electric voltages and currents, and they are by far the most important components of electronic circuits. Every transistor on a chip contains p and n conductive layers made of silicon crystals. They also have an additional layer of silicon oxide, which acts as an insulator. A layer of electrically conductive polysilicon is applied on top of this. Every transistor has 3 terminals. The middle one is attached to the gate, which is the electrically conductive polysilicon. If an electrical charge is applied to only the two outer terminals, electricity cannot flow as the transistor is blocked. This changes, however, if an additional charge is applied to the middle terminal. Electrons from the P layer are then pulled toward the middle terminal and accumulate at the area bordering the silicon crystal and the insulating gate oxide. A channel then forms underneath the gate between the islands of N-conductive material. Electrons can now flow through this channel. The electrical circuit is closed. In this way, the transistor can be switched back and forth between current enable and disable, between 0 and 1, on and off.
Don't buy solar panels. Seriously, there is a very good reason why you're saying this. If you're thinking of...
But how are these layers created on a wafer? The process to manufacture chips from a wafer starts with the layout and design phase. Highly complex chips are made up of billions of integrated and connected transistors, enabling sophisticated circuits such as microcontrollers and crypto chips to be built on a semiconductor surface measuring just a few square millimeters in size. The sheer number of components calls for an in-depth design process. This entails defining the chip's functions, simulating its technical and physical properties, testing its functionality, and working out the individual transistor connections. Special design tools are used to draw up the plans for integrated circuits and develop a three-dimensional architecture of sandwiched layers. This blueprint is transferred to photomasks. Providing geometric images of the circuits, the photomasks are used as image templates during the subsequent chip fabrication process. To ensure that the microscopic structures of a chip are reproduced flawlessly, they have to be fabricated in a dust-free environment with stable temperature and humidity levels. In other words, they have to be made in a clean room. A clean room is a room in which no more than one particle of dust larger than 0.5 micrometers is permitted in around 10 liters of air. This is even cleaner than the air in an operating room. The ventilation, filtration, and supply systems in a clean room therefore have to be extremely sophisticated. Several million cubic meters of air are circulated every hour, and hundreds of air volume regulators maintain a constant airflow. Employees in these production areas have to abide by an extremely strict dress code. They are not permitted to smoke before work or wear any makeup or jewelry. Cleanroom production areas can only be accessed through a special airlock. Chips are built on a base wafer cut from a silicon boule. Depending on their size, several dozen or several thousand chips can be fabricated on one wafer. First of all, the surface of the wafer is oxidized in a high-temperature furnace operating at approximately 1,000 degrees Celsius to create a non-conductive layer. Then a photoresist material is uniformly distributed on this non-conductive layer using centrifugal force. This coating process creates a light-sensitive layer. The wafer is then exposed to light through the photomask in special exposure machines known as steppers. During this process, coaster-size areas of the chip template, known as reticles, are used to transfer the complex geometric patterns of the circuit design to the silicon wafer. The exposed area of the chip pattern is developed, revealing the layer of oxide below. The unexposed part remains as is, protecting the layer of oxide. After this, the exposed layer of oxide is etched off in the areas that have been developed using wet or plasma etching. With plasma etching, special gases bond with the substrate to be removed in the reaction chamber. This enables microscopic layers to be removed in the windows that were exposed and developed in the previous step. Once the photoresist residue has been stripped and the wafer has been cleaned, the wafer undergoes further oxidation. Electrically conductive polysilicon is deposited on this insulation layer. Then photoresist is applied again, and the wafer is exposed to light through the mask. The exposed photoresist is stripped again. Now the polysilicon and the thin oxide layer are etched off. These two layers only remain intact in the center under the photoresist. The next step is the doping process, where impurity atoms are introduced into the exposed silicon. An ion implanter is used to shoot impurity atoms into the silicon. This changes the conductivity of the exposed silicon by fractions of a micrometer. After the photoresist residue has been stripped, another oxide layer is applied. The wafer undergoes another cycle of applying photoresist, exposure through the mask, and stripping. Contact holes are etched to provide access to the conductive layers, enabling the contacts and interconnections to be integrated in the wafer. This is done by depositing metal alloys onto the wafer in sputtering machines. Once again, the photoresist and mask are applied. The unexposed strips remain as is after the etching process, providing a point of contact to the underlying layers. To give the insulation layer above the interconnections the smooth finish it requires, a chemical-mechanical process is used to polish away excess material with micrometer accuracy. These individual steps may be repeated multiple times in the fabrication process until the integrated circuit is complete. Depending on the size and type of chip, the wafer will now contain anything from several dozen to thousands of chips. Individual chips are usually sawed out of the wafer. The chips are not lined up flush with each other on the wafer because tiny parts of the wafer splinter off during the sawing process. A certain amount of space, known as the scribe line, is always left between the individual chips. Test structures are also integrated in this space between the chips and used to take measurements immediately after production. These test structures are destroyed during the sawing process. The size of the resulting chips typically varies between 1 square millimeter and a few square centimeters. The final stage of fabrication is assembly. Here, the individual chips are placed in a package and terminals are attached. The result is a finished semiconductor device, which can be mounted on circuit boards using different types of terminals. Over 1,000 connection contacts can be realized. Here are some examples of ready packaged semiconductor components. Special larger packages are used for power semiconductors, intended for applications such as trains, electric cars, solar panels, and wind turbines. These power semiconductors are designed to switch electrical currents of up to several hundred amps and voltages that run into the thousands. Switching at this level generates high temperatures, and this heat has to be dissipated via cooling areas integrated into the packages. Here you can see some fully packaged power semiconductors. Cutting-edge technology is used for testing at every step in the fabrication process to ensure the highest quality levels and chip yield. Researchers and developers use scanning electron microscopes to repeatedly check the chips at different points in the production process. If we compare today's microelectronics with human hair, we can see just how small these devices are. The equipment used to check components and analyze defects is just as precise. These high levels of precision and quality are essential at every stage of the workflow, from the production of silicon boules through the cleaning room fabrication to quality control, in order to deliver these tiny building blocks that have such a big impact on our lives, today and in the future. After all, demand is rising for innovative semiconductor solutions that make life easier, safer, and greener. For technology that achieves more, consumes less, and is available to everyone. Microelectronics is the key to a better future. Part of your life, part of tomorrow. Infineon.
Okay, thank you very much. This video briefly showed the steps taken in order to build and manufacture a sophisticated integrated circuit. So at this point, I would like to stop here. And again, if you guys have any question, I would be happy to answer. Next lecture, when we come back, we will go through the basic structure of a transistor. And together we learn step by step from the very basic how to build, for example, a MOS transistor, the one that was shown in this video. And we'll go through the detailed operation of a single MOS device. Any question for me? Okay, again, I would like to repeat that all the lectures are recorded. The recorded version of this course, which was offered last year, is also available for everyone's, if everyone is interested. I'm following pretty much the material of last year. I decide to expand upon some of the materials that was covered in the previous year. But after this lecture is ended, I'm going to share with you a number of information, for example, the video, this presentation slide, and also the link to the course that was offered last year on a similar workshop. With that, I would like to wish you a great day and see you all tomorrow.